Hello everyone, I'm Dr. Ashoka Adhikari, and today I'm going to talk about our work which were submitted in IMRC 2026 Symposium Lab 2. Our poster ID is P109 and the title is Facile Synthesis of Nanostructure TiO2 Materials and Analysis of their Property for CO Gas Sensing Applications. So in this research work, TiO2 nanomaterials are fabricated using a green scientific technique called mechanical electrolysis, or simply we can call ball milling technique, and analysis of their property for CO gas sensors. The structural study confirmed the stable tetragonal crystal structure for TiO2 samples, reducing the crystallinity and forming defects at higher milling times. The morphological analysis showed the transformation larger grains, more than 1 micrometer, to nano-sized grains around 100 nanometer after 10 hours of milling process. Verifying the formation of the nanoparticles, the decrease in oxygen content 20% was found with an increase in milling time, creating oxygen vacancy and defects in the crystal structure. Moreover, the band gap values of the TiO2 samples were calculated using reflectance data, where the increment in the band gap value from 2.83 to 3.22 electron volt was attributed to decrement of structural parameters. Ramon and FTR spectra of TiO2 samples revealed an increase in structural defects and lattice disorder with increasing milling times. From bed analysis, greater surface area and pore volume were found for mean samples, which leads to improved interaction with other metals at the molecular level. Nano-sized TiO2 samples allow more interaction with the target gas due to their high surface area, and finally improve the CO gas sensing response for milling TiO2 samples. Many investigation has been reported for TiO2 materials due to their synthesis technique, material characteristics, and applications, especially gas sensing applications, since it contains favorable features like non-toxic, low-cost, biocompatible, and high stability. In this publication, in this work, different TiO2 characteristics have been prepared using physical and chemical technique for the detection of many hazardous gas. Among them, a limited number of research work were associated with the synthesis of nanostructure TiO2 materials using the ball milling technique, primarily focused on the photocatalysis and gas sensors, only for H2S, ethanol, methanol. Hence, in this study, or our study is focused on the synthesis of titanium oxide nanoparticles using the ball milling technique for CO gas sensing applications. The mechanical application is explored using the agate containers and balls. Constant balls to material weight ratio 5:1, milling speed and times, and milling environment. The mechanical milling process for the sample was conducted at different milling times and a constant rotation speed of 500 rpm. You can see the right side in the figure. This is a schematic where we have converted the nanoparticles. We have obtained the nanoparticles of TiO2 with different milling times, where the conditions is 500 rpm rotation time, and we have varied the time 2.5 hours. Here, so the role of milling times on the property of metals and sensing response for CO gas at different operating temperatures and CO gas concentration is systematically investigated in this study, which has not reported previously published research work for the titanium oxide materials. So in the section results and discussions, initially we have presented a axial diffraction results, where we have the patterns we have got from different samples from 0 to 10 hours. We have obtained various peaks, like especially 110, 101, and 211, which are the main three peaks, which we have obtained these. All these peaks are correspond to the tetragonal crystal of the TiO2. Among them, we have also calculated the interplanar distances, and which is also compatible with the PDF of TCPDS number. So after that, we have also checked the morphological. In the down part, we will say A, B, C, D, E, F. In figure 3, you can find initially without milling process, we have obtained geometrical precision, and even the grain size are more than one micrometer size. And after that, the grain size is reducing their size, and finally, we have got in 10 hours, we have got homogeneous grains, and you can see around 100 nanometer, and we can call it from these results. You can say that the presence of nanoparticles of TiO2 or nanograins is obtained. From figure 4, we can see the EDS mapping and EDS spectra. And from the mapping, we have seen the distribution of oxygen and titanium. So for all samples, we have seen the homogeneous distribution. And from the spectra, the peak of oxygen and titanium shows the presence of oxygen and titanium in the samples. And also, we have presented the atomic concentration of the oxygen and titanium for our samples. So in figure 6 or figure 5, you can see further confirm we have checked the 10 results initially for the two samples, 0 hours and 10 hours. And 10 hours we have also seen the very small grains, which is compatible with the same results. And from the high resolution 10 image, we have also calculate the interplanar distances, which is correct, means that the obtained values are near to the we have calculated the near to obtained interplanar distances are near similar to the obtained interplanar distance from the XRD results. So from these results, we can also confirm the XRD structural and morphological properties of the TiO2 samples. Again, we have researched the optical property, and we have calculated the band gap of the samples using the Kubel-Kammon theory, where we use the reflection data. This means our sample is powder, so we have used the reflection data to calculate, and we have seen with increasing the milling time, the band gap is increases also, which is due to the decreasing the efficiency of the samples. And after that, in figure 7, we have also presented the Raman and FTR results. And from the Raman, we have seen the four different peaks. We have B1G, A1G, and multi-phonon process, EG. These peaks are also showing that with increasing the even for this 0 hours, 5 hours, 10 hours, and increasing time, the intensity decreases and the after reaction is increases. So this shows the presence of defects, or we can say low efficiency of the samples. And similarly, for the from the FTR results, the high intensity of the peaks showing that more defects for the samples for higher milling times, which is obtained from the higher milling times. And finally, what we have after that, we have also checked the textural properties, where we have which is bait studies, and from here we have the surface area. So from the mill samples, the surface area is increased from 2 to 18 square per feet, and pore volume and pore size are near, means comparing the results, which is comparable to the mesoporous particles, compatible with the mesoporous particles. And finally, we have checked the gas sensing properties, and we have calculated electric resistance at different conditions. Means initially it is the samples is taken to the air, and after that it will pass the CO concentration. Means from various concentration from 0 to 500 ppm. So we have checked the resistance of the samples, and you can see that the sensitivity in calculate is the difference between the electric resistance of the samples. And here we can see the samples. Then our sample shows the better results normally, and also temperature. So higher temperature showing the better results. So in this case, for example, sensitivity is for the 0 hour samples, but without milling samples, it is around 2. And for the mill samples, it is around 30. So it is from these results, we can confirm that TiO2 nanoparticles were synthesized by the mechanical process, and their properties were utilizing various characterization techniques for their application in CO gas sensors. The structural properties such as XRD peaks, lattice parameters, and interplanar distances confirm the presence of tetragonal crystal structure, which is correspond to the critical phase for both mill and unmilled samples. Raman spectra further support XR results, indicating the formation of additional structural defects in the PiO2 samples at longer milling times. From FPI spectra of PiO2 samples, an increase in the intensity of PiO related vibrational bonds were observed at longer milling times, which may be associated with the structural rearrangement and increased surface exposure of PiO bonds. After mechanical milling, and finally reduce the crystallinity and particle size by generating thermal stress and cracking. From morphological analysis, same and same micrograph the larger more than 1 micrometers and geometry set grains for the unnamed sample, and similarly an irregular shaped homogeneous or nano-sized particles for the mean samples. EDS measurement identifies the uniform distribution of oxygen and titanium atoms as well as the decrement of oxygen content with increasing milling times. And for the band of samples estimated by using Kubeka monk and found in between 2.83 to 3.2 electron volt with increasing milling times. Weight analysis verify the mesoporous TiO2 particles with a plate-like structure with word-shaped pores, where the surface area and pore volume for the new samples are comparatively larger than that of the unknown samples. So it is noticed that the surface electrical resistance values were decreased with an increase in operating temperature due to enhanced electrons excitation in the conduction band and gas concentration by releasing the electrons during surface reaction with CO gas. So we like to acknowledge in sales department and also the department of engineering also in the staff and people who have led to this project, and also the Institute of Physica, UNAM, and the technician from there. So here we are teaching the references and my contact. If you need some, if you have some doubts or something, you can contact me. And thank you very much for seeing this video as well as listening my notes.